I'm very happy to announce Marcel and Weiher that actually wrote a book and released it recently. Please welcome him on stage, and he's going to talk about performance and architecture. Big cheer.
Thank you very much. As Drew just said, my name is Marcel. I work for Microsoft, and actually I did not know we were sponsoring this conference. We're a big company. I work on To-Do, used to be Wunderlist, and we just released a new version last week, so we can finally talk about it. I'm very happy about that. Before that, I've been working in the industry for about 30 years. I'm mostly, well, not mostly, but always very much focused on performance, including at places like the BBC and at Apple and the macOS performance team. And this talk is about sort of the other aspect of performance that doesn't get talked about that much because, yes, we all know how, bring up instruments and then let's go at it. But there's actually another aspect, which is, you need to be able to structure your application in such a way that that will actually work. So this is what this talk is about. So, quick outline of the talk. I'm going to give some general remarks about performance and architecture. And then I'm going to do two examples of how architecture does impact performance and how we can make improvements by changing the architecture or thinking about the architecture beforehand. Specifically, we're going to talk about call return, what implications that might have, the call return architectural style, and about some potential problems with layering and how to get around that. So first, some terminology. What do I mean with architecture? Essentially, architecture is the large-scale structure of software systems, right? And starting at the largest scale, and then going down and into more detail from that. And at that level, a software is constructed of components that do the computation and store data, and the connectors that handle the communication between the components, and therefore define what types of structures you can actually build. Typical architectural styles and sort of types of architecture are call return, which I will talk about. There's pipe and filter, there's event styles, and many, many more, which I'm not going to talk about because that would be a completely different talk. When we talk about performance, oftentimes, we know that as good software engineers, we're being very mature if we hold it off until the end, because that's what good engineers do. And to bolster that claim, we all know how to, quote our Knuth, and, premature optimization is the root of all evil, which is probably the most widely misquoted sentence of the last century, I think. Because if you actually, it's actually correct, it does say that, but there's some context around it which changes the meaning ever so slightly. So in front of that, it's actually the second part of a sentence. It says, we should forget about small efficiencies, say about 97% of the time. So small efficiencies. There's also large efficiencies, right? And also 97% of the time, well, that's essentially all the time, right? So, 97%, that's 100, close enough. Round it up. But actually, that's not what he meant. Next sentence, we should not pass up our opportunities in that critical 3%. So, and in fact, actually, the entire paper this is published in, which is structured programming with go-to statements, is about, yes, you should optimize, and here's how. And in fact, in a little later in that paper, he says, the conventional wisdom calls for ignoring efficiency in the small, so even in the small, but I believe this is simply an overreaction. In established engineering disciplines, unlike ours, a 12% improvement easily obtained is never considered marginal. And I believe the same viewpoint should prevail in software engineering. So please don't use that quote, unless to, say the opposite. So, performance architecture. Unlike the performance in the small that the quote was about, performance architecture is about performance in the large. So that's something we need to deal with from the get-go. And it's also about optimizability. What do I mean with that? Well, you need to structure your software in a certain way that once you've identified those 3%, and it's almost impossible to guess what they will be, your software needs to be in such a shape that you can actually then attack it. Very often, yes, you find it's slow, but at this point, there's nothing we can do except to rewrite. And I've seen this many, many times. And Apple had this very experience. When they released Tiger, they were essentially feature complete, and they noticed it was a complete pig. Very, very fat cat. And it took them 6 months of heroic efforts to get the performance to just sort of basic, somewhat semi-acceptable level, and then they pushed it out the door. And because they never wanted to have that again, they actually created a separate group, which was the macOS 10 performance team, which I then later got hired into, to correct that situation, to always keep up on performance. And starting with Leopard, every other release after that, I think there were, maybe Lion was an exception, got faster on the same hardware. And you only get that through sustained effort. You don't get that through, well, okay, we're ready to ship, let's look at instruments, see what it says. Specifics. So as I was saying, I have two examples. First one is call return. And again, what I mean with call return, well, it's the architectural style that we usually program in, right? And no matter whether we, using a procedural language like C or Pascal, where we have procedures and functions, or we have object-oriented programming languages where we have methods and we send messages, or even if we have FP, which is actually a distillation of that style, what happens is we synchronously call some kind of routine and we get a result back. And we're actually so used to this that it's almost hard to think of structuring your code in a different way. And it's certainly our programming languages make it very hard. So even if you actually like a different style, you will have to implement it using call return, and that makes it kind of difficult. And so, well, we use it all the time, and it works, so is there a problem? Well, maybe, right? Otherwise I wouldn't ask. Oh, there. And so let's look at something extremely simple, right? The description method and protocol that we use in Cocoa to get a string representation of an object. What could possibly go wrong, right? Well, I can give you a small snippet of code with 2 arrays, and that'll crash your program when you get the description. Here it is. All right, I take 2 arrays, I put one in the other and vice versa. So I've created a cycle, Stack Overflow, boom, you're dead. So description can only handle acyclical graphs. Okay, fine, we only want trees anyway, right? Problem solved. Maybe. So what this does, it takes, builds a number of arrays, that you specify, puts them in a specific structure, very simple structure, and then prints the description, and it has some logging around to actually find out how much memory we're using. This will not crash the program. It's more likely to crash your machine because you're going to run out of swap space. So very quickly, you get the number of arrays you're supposed to create from the command line, set up some memory statistics, logging, and then the nasty trick is here. We put each array, the previous array, into the next array, and that's all we do. And that means we have a degenerate tree that has 1 array for each level of the tree. And so what happens? Well, this happens. Let's see if this, are colors readable? Can you? So the upper line that kind of rockets off into the sky, that's green. That's the total memory used. And the little line at the bottom, the blue line, that's the actual amount of memory that's required for the result. And the x-axis is how many arrays are we using. It stops at 50 because if I have more, the graphs diverge so much that either it goes off into the stratosphere or the x-axis just is the same as the blue line. And if you specify something like 2000, that'll have your machine swapping for quite some time, and after that you might run out of swap. And so why is that? Why do we have so much temporary memory use when the problem is really simple? And it turns out it's because of the call return architectural style. Because we have no context, we need to return a complete result with every call, every level has to then incorporate all these partial results into the next level of the result. And that means what you get in terms of memory use, you get the requirement is total width of the result times depth of the tree. And of course I was nasty and just said these are the same because I just make this degenerate tree. So in that case it's n squared. And that gets quick very, very fast. So how do you solve this? Well, we need to change from this idea of having a result that we return, and we need to get something more like a pipe and filter system, where we continuously write partial results to a target. But of course, since we're in a call return language, we have to implement it as a method. I'd rather write it differently, but again, that's just what we have. So that's the method. I hope it's readable. So instead of returning a result, this method gets a location for the result as an argument, a buffer, and then we just start writing, right? We just write this opening bracket, we then loop over our contents, and then recursively write the result, tell the sub-object to write its result into the existing buffer at that location. So none of this copying the temporary results around. How does that work? Nicely. Okay, now these are the same two graphs, essentially. So it's temporary usage and the total size. And essentially they're the same, except that for the temporary usage, you get a little step function because malloc actually has bucketing, right? So you can't get the exact amount, you get a little bit more sometimes. And you'll also notice that the x-axis labels are slightly different, right? They start at 5,000 and end at 40,000, and we have about the same amount of memory used as we did before when we were going up to 50. So, well, you know, description is not really interesting. I used it as a nice, very crisp example because it's so small. Does this affect other APIs? And of course the answer is yes, right? Any type of API that has this call return structure will have this problem. And the example that every iOS developer knows is an XML document, because it's not on iOS because it uses too much memory. That's why they kept it a while. But of course, the replacement APIs that we do have the same problem. NSJSON serialization, NS property list serialization all have this problem in the API. You cannot create or provide alternative implementations of these APIs that don't have this problem. Keyed archiving is different. It actually has the proper API, but underneath they're using the same structure. So there you can actually provide an alternative implementation that works better. There it's possible. With the others it's actually not possible. You need to start using a different API to avoid all this these temporary allocations. And of course, as I mentioned, the alternative is to adopt a more pipe filter architectural style. And I've done that using filter objects where each filter essentially encapsulates an operation pretty much like a Unix filter. And they communicate with each other using a common protocol. It's write object. Instead of, you know, in Unix you have write a line of strings or read a line of text. Here it's just write an object. And since it's a common protocol, you can stack these any way you want, recombine them into pipes, and of course you can do incremental results because you're not returning the result, you're writing to a target, and that means you can just keep doing that. And because it's not synchronous, you're not waiting for the result. It's in some other section. It's actually also really wonderful for when you need to write asynchronous code, such as network stacks. And for example, the to-do network stack on iOS and Mac is written using these pipes and filters. And it's wonderful. So, call return, yay. Oops. So I'm going back. Okay, so now let's talk about layering. Most of our software systems are layered. And again, we're so used to it that we just really don't think about it that much. And I got interested in a specific example when I looked at the issue 4 of Objective-CIO newsletter blog, and that was on core data. And they had a special, one article was on importing large data sets. I'm like, large data sets, that looks interesting. Let's see what happens. And the idea is, You wanted to have an iPhone app that can do searches for public transport near your location at the current time, right? And to do that, you need to have and do this offline. And to do that, you need to have that information, which a lot of public transport companies now provide in Google's general transit feed specification format, which is a comma separate values file. And I got those from our Berliner Verkehrsgesellschaft. And it's a lot of data. It's the total size of the files is about 130 megabytes of comma separate values. And then that gets, in the article, that gets converted into an SQLite database using core data. And then the database is transferred to the phone, probably not over air, because 130 megabytes, people would probably not like you. And then you can query the database. And performance for the queries was kind of okay-ish. So sort of half a second for a time plus place query, which, it's not bad, but of course we'd like to have 100 milliseconds, so response is instantaneous. Transforming the data was 22 minutes, which I thought was kind of excessive. And I wondered, well, can we do better? And I really couldn't figure out why, because there's nothing wrong, right? It was an application model, it was sitting on core data, which was sitting on SQLite. And all of these are best of breed, right? SQLite is a super fast database. I wouldn't know where to begin to make it faster, and I'm pretty sure I couldn't do it. I know some of the people on the core data team, super smart. They have done, years of performance tuning on this stuff. Maybe you can tune the stack a little bit, but experience tells you that that'll, be a couple percent. Now, let's not be too condescending about a couple of percent, because, right, 12%, we shouldn't belittle that. But still, 22 minutes is 22 minutes. So what to do? Well, change the focus. Hexagonal architecture says, let's not layer these things on top of each other, on top of the sort of I/O layers and stuff, but rather let's do this from the inside out. That means we focus on the in-memory model, and then we attach everything else on the outside. And that gets you a slightly different focus. So let's look at the actual data model that we need to implement. So here's a sample, actually two samples, one from the file defining the stops, which is actually not that large. There's about 16,000 stops. So, that's not really that much. And each stop has an ID, which is an integer. It has a name, string, and it has some coordinates where it's located. In terms of just bulk, the real meat is in the times. That's 3 million entries. And it has a arrival time that we're not interested in, the departure time, and the idea of the stop, where it's located. So that's more interesting. So we leave the stops just as objects that we have, and for the times, we're going to need something more interesting. So interesting only in terms of we don't use the standard modeling techniques that we use, because actually it's a very simple model, right? Every stop is just, every time is just the actual hour and minute. And since we have, an hour only has, a day only has 24 hours, that means we can model it in 5 bits using a bit field in C, and a minute, there's a 60 minutes in an hour, so that's 6 bits. And since we only have about 16,000 stops, 20 bits is quite sufficient for the stop index. So that means we can have the whole thing in under 32 bits. That's nice. And we put in a struct, and so we can construct arrays of these, right? And now to actually look them up quickly, since we're looking up by time, and time has this wonderful property, especially at our resolution, that it's just small integers. We can just use an index straight array indexing. So essentially the index is just, we have some buckets in our array, and we store the start location of those buckets in a two-dimensional array. And then if we want to look up a time, we just index into that array by hour and by minute, and there we have it. And then we go up and check out all the stops in that bucket. Unfortunately, the data does not come sorted in that way. It just comes in essentially random order, so we have to sort it. Well, that we all know, n log n is sort of the optimum for sorting, so that's going to take some time. That kind of sucks. Except there's a small footnote there. If you're sorting small, especially densely packed integers, you can do bucket sort, and that's linear. So that's what we're going to do. So this is the first part of that algorithm. Starts off just with some allocations. And because we have structures, we can just allocate them in one fell swoop instead of lots of little allocations. That makes it very fast. The next thing we have to do, we have to size the buckets. So for each bucket, we have to figure out how many elements are going to be in that bucket so we can pack them tightly, which is what we want to do. And then we accumulate those sizes in order to get starting offsets, right? Because if I have something, 5 elements and 5 buckets, and the first one is 5 elements, and the next one is 6 elements, and the next one is another 5 elements, and the first one is going to start at 0, the next one is going to start at 5, and the next one is going to start at index 11. So I just have to add these up, and it's really, really trivial. And then I do the actual sorting, which is this little bit, and it's really simple. I just iterate through all the stop structures, and I just put the stop struct that I currently have at that index location. And that's just a double indexing operation, so it takes essentially no time. Finally, for some reason I can't actually quite remember, I then sort the stops that are in a particular bucket by their ID, and I just use a normal merge sort for that. But that doesn't really matter because actually these are all really small buckets, so the n log n factor here is tiny. And what that means is that this entire algorithm, so once we have it in that initial structure, actually only takes 280 milliseconds, including using fwrite to write the binary representation out. And then when we want to use that data on the iPhone, we can just memory map that into memory because there are no pointers in this structure, right? That we might have to fix up. And also, this is not a public format. There's 2 private entities that communicate over a channel that we will both control. So we can use a binary format. Might want to add some versioning, which this doesn't have. But other than that, we're fine. And then once we have that mapped into memory, we can just use memory access, as I described before, and the results are pretty good. So the time to query dropped from half a second to 58 microseconds, which is about 8,000 times faster. The time to create is less than a second for everything, including the comma-separate values, which I'm going to talk about in a second, down from 22 minutes, so that's a factor of 1,000. And the size of the file is 12 megabytes. Rather than 120 megabytes, so that's 10x. And actually, that we might, if we actually compress it, we could probably send that over the wire and keep the app over up to date with the information that we want. A quick note on, so that's more than 12%, by the way. And the one slightly sub 1 second time, again, it includes the parsing the comma-separate values. In the initial implementation, that took 18 seconds, which, compared to 22 minutes, that didn't matter. But when we were down to 280 milliseconds, that kind of did. So there was another factor 30 there that I'm not going to talk about in detail. But it's in the book. Anyway, but the thing is, the reason we could do these optimizations is because we broke up the layering, right? We did not assume. Despite the fact that all of these are best of breed, the best you can do, and the architecture is reasonable, there's nothing wrong here, right? We were able to do 1,000 to 8,000 times better by switching around the architecture. right? And then once we have focused on that application model, the other things can just sort of be on the periphery and don't matter that much. They don't control the rest of our application, kind of similar to what you just talked about with your storage, right? We want that to be the central, the model. And then, yeah, I used fwrite-mmap because it was fast and convenient, and it's a single function each. But if you wanted to, you could probably use other serialization formats. That would also be reasonably quick. And that's really all I have to do for today. There's a lot more I wish I could have talked about because optimization is a huge field. There is a lot of why is it this way? What are the hardware trends that make this possible? But what I want you to take away from this talk is that really that architecture matters a lot. We keep getting told that Apple tells us what the architecture is and that's it. Don't buy that. You really, if performance matters, and admittedly there are many cases where it doesn't, but if it does, architecture matters a whole lot. And we talked about a little bit about what can happen if we just follow the call return model blindly, and what we can do about it by getting more pipe and filtery. And another one of my favorites is the hexagonal architecture, which I've been using for upward of 15 years now, and it's always been really great. The initial focus there was really testability, but it's also been really amazing for performance. And of course, think about when you build your architecture and initial architecture of your application. Don't tune at that point, but make it tunable. That's the point, because you don't know what to tune yet. But you will know once you're done, and you need to set up the architecture in such a way that once you have the information, you can still make optimizations. And that's it.